Hello, this is Jake Sherwood, and this is Lab 4 Circuits. So, for the introduction, the purpose of this experiment was to predict the behavior of circuits containing resistors in series and parallel. Use the multimeter to measure the actual values of conventional current and potential differences in the circuits, and also examine the behavior of ohmic resistors and capacitors. Some of the fundamental principles that were used in this lab are Kirchhoff's law, conservation of charge, Ohm's law, steady state circuits, the loop, and node rule. For the main results, we have a potential difference of 0 volts, current equals 0.02 amps, and the RC was 6 seconds. Some of the assumptions that we made during this lab were that we had negligible resistance in wires and ammeter. This is because that we were using a simulation. So the typical resistance in a real life model would not have shown up. We also have change in the V capacitor plus a change in V resistor equals 0. And for our system, that would be the circuits, and the surroundings would be everything else. For the experiment, we have our first step was to set up a simple series circuit on the simulator with two 1.5 volt batteries, two resistors, and two ammeters. Then we needed to predict I1 and I2, and we found this to be 0.02 amps. And for the reversed ammeter, it would be negative 0.02 amps. And then we needed to close circuit with wires for step 2 and measure the potential differences. For the RC circuit, we had two steps to the RC circuit. So we had one with a 10 ohm bulb, a 9 volt battery, and a 200 MF capacitor. And then we repeated this experiment with a 20 ohm bulb, and the rest was all the same. And for this, we had a current of 0 amps for both of these. But for the charging time, we had less charging and discharging time for the 10 ohm. As you can see, charging time was 15.6 seconds and discharging time was 15.3 seconds. And for the 20 ohm, it was 26.3 seconds and discharging of 27.8. For some of the conclusions of the lab, what if we were doing this lab in real life and using an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked up to it? If you did this lab with real circuit components, access the virtual circuit and see if you can determine how it would behave differently than real ammeter you used. The simulated ammeter has no resistance, whereas the real life model would likely have some resistance, which would lower the calculated current. And then for the next one, we have, what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor reach full charge? And the answer would be a real battery would not charge the ideal calculated time of 6 seconds like this simulation because it wouldn't charge immediately. Some of the potential errors in this experiment was the simulated model doesn't reflect the realities of a real simulation, as I explained earlier, because it doesn't account for resistance in the wires. And also the timing of discharge capacitor could be skewed, and the calculations also could be wrong due to random errors like rounding errors. Some of the conclusions in the lab, we have capacitors hold charge and discharge while current decreases over time until steady state. Calculated resistance values are greater than resistance values in the PHYS simulation. And we also have the findings support the loop rule, and that's the lab.